All right, so it's my pleasure to introduce Zinn-Justin from University of Melbourne, and he will talk about Schubert calculus and quantum integrability. Paul was unhappy that he gave this talk several times, and people heard this talk. Right?
I'm not happy. I'm always happy to talk about it. You might be,
but I think everyone should be happy because it will give us a chance to actually understand this. This is a big subject, and we're scratching the surface of the iceberg.
Thanks for the invitation. Yeah, this is joint work with Allen. It's something we've been working on for by now six, 7 years to try to apply ideas from quantum integrable systems to a Schubert calculus, which is an area of enumerated geometry. And I usually always start with a very elementary introduction to what is Schubert calculus for those of you who've never heard of it. So yeah, I'll talk first about Schubert calculus. That's pretty much the plan you can see on the top. Then I'll try to not get into the technicalities, but at least have an overview of why quantum integrable systems appear in this story. And then the last part will be some actual applications to computing stuff, basically. So first, why is Schubert calculus? Is there any way we can remove that thing there? That's
oh, yes.
Because it's kind of blocking the first line, which is the important line.
Well, yeah.
Can I? Okay. Yes. All right. Yeah, so Schubert calculus is it's a branch of enumerative geometry, which is about very simple questions like the following. So usually at this stage, I'll show you a nice demo, but we won't have that today because this is going to be a low-tech talk for a change. You take 4 lines in 3-dimensional space, 4 straight lines. So this is the feature of Schubert calculus. It's all about just enumerating things which have to do with like straight lines and planes and all just linear subspaces or affine subspaces, but no fancy. So it's very elementary geometry in a sense. So you fix 4 given lines in general position in 3-dimensional space, and you ask the following question, which Schubert answered already in the 19th century: how many lines intersect all 4 given lines at once? Right. So if you actually do it with real lines and fit them, you'll find that the answer actually depends on the configuration. The answer can be 0, 1, or 2. But let me immediately say we always work in complex space in which all equations, an equation of degree n has n solutions, at least generically, and solutions if they are not degenerate. So if you do it in complex space, the answer is always there are 2 lines going through 4 given lines in the general position. And of course, I'll show you in a sec how Schubert solved this problem using elementary ideas. But the way we think about it in modern language is that we're actually doing calculations in the cohomology ring of the space of configurations. So what is the space of configurations here? It's always convenient to projectivize by just adding points at infinity, as we always do, so that the space of configurations is compact. And then if you think about it for a sec, the space of lines in 3 space, in projective 3 space, is nothing but the same as so it's called the Grassmannian of lines in projective 3 space. And yeah, let me just for now give it a name. It's a GR1P3, or if you deprojectivize, it's like the space of planes going through the origin in C4. That's the same. So GR2C4 or GR1P3, depending how you think about it. So there's a name to the space of configurations, which is Grassmannians. So you're doing computations in the cohomology of the Grassmannian, basically. And I'll say a little bit more about that in a second. But before I go on, let me point out that you can generalize immediately this problem by obviously changing the numbers in the problem. You don't have to do GR24. You can do GRKN, which is vector space subspaces of dimension K and Cn. Or you can even do more sophisticated things like partial flight varieties, which are now you have subspaces, but they're embedded, they're nested inside each other with some choice of dimension for each of them. So we're going to be dealing with these varieties. They're all projective smooth algebraic varieties over C. And in each time we want to consider their cohomology, and we want to do some calculations. So what kind of calculations are we doing? Well, let's simplify for another problem. We had 4 lines in 3 space, but let's only take 2 of them at a time. We're going to first take 2 of them and then the other 2, and then we'll glue them together. So let's just take 2 lines in 3 space in general position. And the way it always works is we're going to study like subsets, basically, or subvarieties, if you like, of configurations which have specific properties. So for example, for each such line, we can say, let me define yi to be the subset of all the lines that intersect. So y1 would be all the lines intersecting L1, y2 all the lines intersecting L2, and both of them define subsets, let's just say, inside GER 2C4. And the point is that even though as sets they are different, they are homologous. One way you can think about it is you can always move one line to L1 to the other line L2, so you can kind of deform continuously one into the other. So they define the same element in homology or Poincaré isomorphism in cohomology. And this element, for reasons that I don't want to insist on right now, I would call S01, 01. So in particular, the point being that if you're trying to compute now the intersection of the two sets, which means the lines touching both L1 and L2, that's ultimately what we're trying to do here. All you're doing is you're trying to compute the square of an element in cohomology, because intersection kind of like transverse intersection in cohomology is like taking the product. So we're trying to compute the square of an element in cohomology. And so, okay, so now, that I'm doing things in a completely anachronistic way, because this is, of course, the 20th century interpretation. Now let's go back to how Schubert solved it. So Schubert had the following idea. He said, well, it's probably not so important where exactly the lines L1 and L2 are. So how about we take a slightly singular, but not too singular configuration? And all the art here and the black magic at the time was what exactly we mean by that. But he had the idea that it's probably all right if we actually choose the lines L1 and L2 to be intersecting. So now imagine you have two lines that are intersecting, and you're asking the question, same question, how many lines are there? What are the possible lines that intersect two lines which happen to be crossing? And that's a much easier problem. This is already elementary geometry. If you have two lines, a third line crossing the two lines, either it's in the plane of these two lines, or it goes through the intersection of the two. So there's a nice binary answer, which is so following Schubert, we say, well, if the two lines intersect, then we know exactly what y1 intersect y2 is, and we hope that the answer is not too different than the generic case where they're not intersecting. And so the two possibilities, either lines in their plane or lines going through the intersection. And of course, these are not disjoint possibilities. That's, of course, the case where it satisfies both. So I'm writing here under the union thing, the intersection of the two is lines that are both in the plane and going through the intersection. And so in cohomology, we can ignore that feature, and we can just say, well, roughly speaking, union is like sum. And so I'm just going to say that the square of this class is the class of this thing plus the class of this thing. And each of them are kind of really nice, simple objects. And so we're going to give them some more names to them. One of them we're going to call S1001, and the other one S0110. And that's a correct identity in the cohomology if these elements are defined correctly. Now, immediately, I want to say that there's always a refinement of a cohomology, which is a K-theory, in which we actually do care about issues of the fact that this is not a disjoint union. So in K-theory, you say the same thing, but you say, actually, I should subtract, it's like exclusion, inclusion. We're going to subtract the intersection, because otherwise we counted it twice. And the intersection is also a Schubert class. It's also a natural thing, lines going through one point and sitting in one plane, and we call that S1010. So cohomology is a slightly more advanced version where you have some corrective terms in some sense. Okay, now homework, finish the exercise. Now we've done it with 2 lines, you have to do it with 4 lines. So obviously you can play the exact same game. Assume that these 4 lines, there are 2 of them intersecting at one point, 2 of them intersecting at another point, and then you're trying to compute the number of lines going through all 4, and you'll see it's not very complicated. And you'll find the answer of 2. And that's the same as computing the 4th power of this S01 as S01 if you prefer. So elementary, geometry. And now we want to generalize this. So let's for now stick to the Grassmannians. So now let's consider GER Kn, so general K planes in space. As always, there is going to be this natural, basis, basically. So in other words, we have to somehow organize it. It's a space, let's say let's do everything over the complex numbers, do not worry about it. Or you can do it integrally, but I don't really care. But if you do it, if you tensor the cohomology with C, let's say it's just a vector space, and you have to find some natural basis. And there is a natural basis, which is the generalization of the one I showed before, which is called the Schubert basis. And the basis vectors are Schubert classes, and which are denoted as lambda, where lambda in general is a binary string with k zeros and n minus k ones. So that's why I use this kind of notation here with zeros and ones. This is the special case where there are 2 zeros and 2 ones. So in general, you can define a very natural basis. This is very, again, elementary geometry, a basis of Schubert classes. And what we're really trying to do is basically just compute the structure constants of this commutative algebra. So yeah, so the cohomology is commutative for boring reasons that it's only non-zero in even degrees, so it's just a commutative algebra. Same for the K theory, only the K0 is non-trivial. So that means it's just a commutative algebra with a preferred basis. So you can just literally expand the product of two elements of the basis onto the basis, and you have those structure constants C lambda and nu, and you want to compute them. So that's the general problem we're trying to solve. Now, in the particular case of the Grassmannian, this has already been solved in the 20th century in many, many ways, in fact. It's in this particular case, yeah, so I should also point out that for people who don't like geometry and direct networks, you can also recalculate this purely in terms of polynomials. So for example, in the case of the Grassmannian, this is the same problem as computing the product of two Schur polynomials and expanding it into Schur polynomials. And this problem in itself has many other connections to representation theory, because Schur polynomials are characters. So there are, in the particular case of the Grassmannian only, there are many different ways of thinking about this particular problem. And that means there are as many solutions as there are ways of thinking about it. So irrespective of the geometry, already Littlewood and Richardson thinking about the tensor products of GLN representations or Schur functions, they already formulated a certain way of computing these numbers. So we're talking about actual combinatorial rules, which means they said that C lambda mu is the number of a certain type of objects, some tableaus, satisfy certain properties. So it's an explicit combinatorial description of C lambda mu as counting some objects. Yeah, so in particular, these are non-negative integers, which is not completely obvious a priori. The integrality is obvious. The positivity is geometrically is this kind of like it's also natural, but it's not completely obvious a priori that they're non-negative integers. And the rule later was reinterpreted in terms of the Grassmannian in the 40s, and then eventually Schützen-Berger proved rigorously that rule in the 70s. Anyway, there's a long story that throughout the whole of the 20th century. But I'm interested in a particular version that was introduced by my collaborator, Allen, and by Terry Tao. So it's a strictly equivalent rule. In fact, there are bijections in all kinds of ways, but this is the one I like. It says, to compute C lambda mu, you have to compute the number of puzzles with certain size. So what are puzzles? Again, that's the part where usually I show examples rather than read all this text on the slide. Okay, well, we'll read the text on the slide for change. So a puzzle is an assignment of labels 0, 1, or 10 to each edge of a triangle, of a equilateral triangle, which itself is made of like little. So it's basically part of the triangular lattice, which forms an equilateral triangle. And on the boundaries, you only have zeros and ones, which correspond to the lambda, mu, and nu. So the three sides of the puzzles are labeled with the binary strings, and these sides can have zeros, ones, and tens, but only according to certain patterns, which are a bit magical. In fact, at the time, I think it was completely magical. You have exactly, I don't know how many pieces, 3 plus 3 plus 1 plus 1 plus 1 plus 1. These particular patterns of labels on every edge. But maybe this is the part where I'm getting excited. Maybe if we click on example, something is going to happen. No internet. No? What is it?
No.
Oh, it's. Why not?
Your site is not safe.
My site is not safe. Can we just?
Well, you can probably ignore it.
Yeah, can we ignore it? My site is completely safe. Принять risk. Yes, I'm a risk taker. Here we go. All right, so that. All good. So fortunately, the internet has come to the rescue. And so these are, for example, the two puzzles with size 0, 1, 0, 1, 0, 1, 0, 1. And at the bottom, you recognize our 2, 0, 1, 1, 0, and 1, 0, 0, 1. So that's exactly the example we had before. You know, it's the lines going through two given lines. And the computer has drawn them correctly. I mean, there's a bit of a glitch here, but you can see these are like zeros and tens and ones in certain configurations. And all good. So that was the original paper of Knutson and Dow, and they were interested in this for completely, for a different story. This is the whole saturation conjecture, which is not relevant today. And later, Vakil, already in the context of Schubert calculus, realized that if you only produce an extra piece which is 10, 10, 10, so you change a little bit the rule, and you get this time the rule in K theory. And let's see if will it tell me again that this is, no, this time it's happy. Okay, so let's do it again. Let's have the computer painfully compute. Yeah, so now if you do it in K theory, you get a third one, and that's 1, 0, 1, 0, and you're happy. That's the extra term that says that, well, actually we overcounted a little bit because, you know, there are lines that both, you know, go through a given point and are inside a given point. And this one has the extra 10, 10, 10 piece in the middle, this yellow piece. All right, so far so good. And later with Allen, we realized that actually, even if you include both the 10, 10, 10 up pointing triangle and the down, so I don't know if you see the difference. The orientation of triangles is important. So you can't just arbitrarily, you can only rotate them by 120 degrees, not 180. And if we introduce both of them, these are still the structure constants of a commutative algebra, which is not at all trivial. You know, if you randomly try to set up some rules, these C1Ws will not be structural constants of a commutative algebra. It has to satisfy certain, you know, there are some constraints, and this is still satisfies all the necessary constraints. And so we realized that there was more to it than meets the eye. So at this stage, the question is, what exactly are we doing, and what does this have to do with quantum integrability, which at the time, of course, was completely unknown. Well, until my paper in 2009, it's completely unknown. Okay, so we're switching gears now. We're going to talk about integrable systems. Part number 2. So yeah, where does thank you, my slide. Where does quantum integrability come into play? So for Grassmannians, the problem has been solved. Okay, it's been solved in 50 different ways. Okay, there's really not that much more you can say about it, except maybe just this last remark here that if you introduce both of these two tiles, then this is still a commutative algebra. So there are, even in this case, there was still a little bit of a mystery. But if you ignore that and just go back to, okay, computations in the cohomology of, say, Grassmannians, okay, that's over. But you can also compute, you can try to play the exact same game for the cohomology of, say, flag varieties. So which would, you know, in terms of geometry, would correspond to more complicated configurations they're trying to study with now nested spaces and so on. And in this general framework, there is no nice answer, let's just say, to the problem of Schubert calculus. Now, I recently watched this talk by Igor Pak, in which he spends a lot of time trying to understand what is a nice, you know, what's the nice solution to the combinatorial problem. You know, here, I mean, I guess in some sense positive and also probably efficient from an algorithmic point of view. I'm being intentionally a little bit vague because otherwise there are trivial answers to this problem. You know, almost tautologically, you can solve any problem in a sort of tautological manner, but I really want an explicit combinatorial and kind of nice answer to the problem. So this is still an open problem very much. And so, as I said, my interest is in applying methods from quantum integrable systems. And again, I'm being slightly anachronistic, but in retrospect, the way you should think about it probably is go through the logic of why there is a connection between algebraic geometry and quantum integrable systems. And that's been by now fairly well understood through the work first of Nekrasov and Shatashvili in the kind of physics literature, and then the work of Okunkov and collaborators, and then the work of Rumani, Tarasov, Varshenko, and so on. So we know in some sense that indeed there is a deep connection between the cohomology of those various spaces and quantum integrable systems. So there is one piece of the puzzle, sorry, bad fun, that is by now pretty clear. It was not at the time that we started working on this, but now it's pretty clear that there is a simple logic to why quantum integrable systems should appear. But actually, it's not enough. The point is that this is actually not enough to solve the problem above, because really in the framework, in all these frameworks of these various people, you don't really, it doesn't really naturally tell you how to take products of classes at a very technical level, basically. So of course, you can see the sort of algebra structure in there, but it's not in an explicit manner. You can't literally take just two Schubert classes and take their product and expect that the quantum integrability will give you the answer. So you need some more ideas. And so the idea I had completely independently of that, in fact, this is earlier than a lot of the work that I just cited, is that maybe puzzles themselves are also an integrable system, a different one than the one that's directly connected to the cohomology of the configuration spaces. And then, of course, that begs the question, what the heck? Now there are different quantum integrable systems. How are they related to each other? What's the geometry behind? And so by now we understand the answer to all of these questions. And so that's my work with Allen. So in particular, as a corollary, we managed to get a whole bunch of new product rules for Schubert classes and generalizations in partial plug varieties. So in certain partial plug varieties, I'll give you the list if you care about such like record, keeping track of who did what, but it's not so important. But the general philosophy by now is pretty clear, I would say. Okay, I may skip in front of this audience the historical slide. As I said, this is actually the talk I should have given on Monday. This is a historical talk, so there's a lot of history about the Baxter equation, which I may skip today because I don't think you need to. I think most of you already know about the Baxter equation, about the Leningrad school whose representative is right here in front of us, and then also the Japanese school of quantum groups and quantized advanced algebras. So the short answer is yes. So the integrability will appear through the representation theory of quantized loop algebras, to be very specific. For the experts, there's never any central charge in what I say. So there'll be a lot of representation theory related to quantized loop algebras, and maybe I'll not spend any time on this slide. All right, so let me remind you more or less what the Baxter equation looks like. At the most naive level, and the way we think about it, it's just a certain trilinear equation for a family of linear operators which depend on a spectral parameter which lives on some abelian curve, and in my case it will always be just the multiplicative group, and I'll do everything over the complex number, so it's just C minus 0, so not a non-zero complex number. And so V here is just again complex vector space, and the identity itself is very easy to understand graphically. The way we always represent it is a bread-like fashion by saying, well, if we have one such operator, let me define a whole bunch of them are check sub I, which will be defined as follows. It's just R check, but just acting on, so it's an operator now on V tensor N, where N is some arbitrary integer. And the action of this R check I is that it acts as R check only on spaces I and I plus 1. So on the I and I plus 1 copies of Cn, and it acts as the identity everywhere else. And the choice of the parameter has to be dictated in a kind of consistent way. That means parameters are attached to two lines graphically. So yeah, so graphically we represent each vector space by line with the parameter Zi attached to line I. And whenever you have an R matrix, you represent it as a crossing, and the spectral parameters kind of cross to, they kind of follow the lines. And when there's a crossing, the two spectral parameters, sorry, the two parameters Zi, which I call spectral parameters, get exchanged as well. And the value you put as the parameter for the R matrix is always the ratio of those two spectral parameters. So I'm only ever dealing with solutions of the Baxter equation which satisfy the difference property. That means in this case, it only depends on the ratio Zi over Zi plus 1. Geometrically, that's always the way they appear. That I'm not clear on if you take solutions which do not satisfy the difference property, what that means geometrically. So we'll stick to that kind of solution. Anyway, and then the Baxter equation then takes essentially the form of the braid relation. So you take n equals 3, and then you just write that these two pictures are the same. So each of these crossings is an R matrix, so it's a trilinear equation. And so now the next question is, can we actually solve this equation? And the answer is yes. And this is precisely the connection with well, there are many ways, of course, you can solve it. This was a whole business for a time. But one way, which is probably by now kind of the conventional way to think about how to solve the Baxter equation, is via quantized loop algebras. So what I quantize with algebras, you start with G, which is a, let's say, a simple Lie algebra. Then you take its loop algebra, G bracket Z plus minus, so just G cross, say, C of cross the just long polynomials in one variable. So this variable is secretly already, in some sense, our spectral parameter. That's why I use the same letter Z or Z. I guess I'm Australian now, I should say Z. And anyway, so then that's a Lie algebra. Then you take its universal enveloping algebra, and finally you deform it. So there is a one parameter family of deformations, and the deformation parameter is usually called Q, the quantum parameter. And there's also, so they're algebras, but they're actually half algebras. That means there's also a coproduct, which means you have a way of taking tensor products of representations. And then you have they're quasi-triangular, which means also you know how to switch, when you commute two factors of tensor product, you know how to get the isomorphism that switches them. And that's exactly what the R matrix does for you. So let's see what else. Yes, so in practice, does it mean? Yeah, so there are some technicalities which I'm hiding, but roughly speaking, because they're probably more like pseudo-triangular algebras or something, but let's not worry about that. So in practice, that means if you have finite dimensional representations of this quantized group algebra, then there are explicit interpolars between Px tensor Vy, say, and Vy tensor Vx. And this is exactly this archetype of x divided by y that is a solution of the Young-Baxter equation. And typically, yeah, it's an analytic function of, except maybe at some points, and satisfies the Young-Baxter equation. And so more generally, if you have a whole tensor product like those n lines, that means all these R check I, you can think of them as little operations that kind of allow you to commute inside a big tensor product the factors. Well, that's my one slide summary of the representation theory of quantized loop algebras. The second ingredient we need is the Nakajima quiver variety. So in other words, that's the part that we know geometry, that's representation theory. But we know from Nakajima that these quantized loop algebras occur naturally in geometry. And these quiver varieties are kind of a natural framework to see this connection between integrable systems and geometry. They're not like it's not the most general framework in which such a correspondence should work. In fact, we know examples outside, and there are various ways we can realize various solutions in this theory to enlarge the space of the live varieties. But it's a very convenient framework in which we understand pretty much everything. So, and for the purposes of today, this is all we need. We'll stick to Nakajima quiver varieties that will already give us quite a bit of freedom to. There's going to be a lot of choices to be made. And that's going to give us a lot of, well, Schubert diagonal also is pretty hard. We can talk about how to go beyond, but maybe not today. Okay, so the basic data in the case of a Nakajima quiver variety is obviously a quiver, and in fact you don't really care about the orientation, only the underlying graph matters. And then there is a bunch of integers associated to that quiver. In fact, there are two. This slide oversimplifies a little bit. There are usually two sets of dimensions: the frame dimension vector and the gauge dimension vector. But I guess in this slide, I'm implicitly assuming that the second parameters are kind of free or whatever. So I'm simplifying a little bit the story, but basically to a quiver and some dimension vector is associated with a certain smooth weather projective variety, which I know NQ of W. And for now, I only care about one case, which is the case where Q is the following quiver. So it's some oriented version of the AD thinking diagram, if you like. It doesn't matter which. Oh yeah. So the reason it doesn't matter which orientation is that the first thing you do in a quiver variety is you kind of take the tangent bubble and all edges are doubled. So the original orientation is essentially relevant to signs and which can be absorbed. So it doesn't really matter. So secretly all edges are doubled. So you have an AD diagram, and you also have one extra vertex, which is a bit different than the others. This is the frame vertex, and then this is where this is the number W here. In this case, there's only one such number. It's n. So you have D vertices, and then you have one special box which has the number n in it. And the claim is that in this case, M, okay, that's the part where, yeah. The M is the union of all the D-step-like varieties. So it's exactly, sorry, the potential bundles are all D-step-like varieties. So let me decode what I said. So first we start with this space, which is the space of all vector subspaces of Cn when there are G of them nested together. That has several different components depending on the dimension, but that's okay. That's the part that I ignore on this side. And then you take a cotangent bubble, and I claim this is exactly the M you get. And so you can see how this is already a little bit to do with our original problem, because we cared about this space, but then the geometry suggests that maybe that's not the right space to consider. We don't want to just take partial flat varieties. We should consider the cotangent bubble, because it's a symplectic space, for example, so it has lots of nice properties, which you wouldn't have if you didn't take the full space of the cotangent bubble. There are other things to notice is that there is naturally, so in other words, we want the content parameter appearing somehow and also these spectral parameters that one is up to Z. And they also occur very naturally in the fact that there is naturally a torus acting on this variety. So whenever you have any flat variety of this type where you have subspaces of Cn, you have a natural action of GLM. And in particular, you have an action of the Cartan torus of GLM, which is this diagonal matrices. So there are n-dimensional torus. And there's always an extra scaling action, which is where when you have the cotangent bubble, you can scale the fiber of the cotangent bubble, and that gives you an extra C-star action. So you have an n+1 dimensional torus acting on M. And that means in terms of, if you know anything about equivalent cohomology, you know that each degree of freedom of the torus will give you one parameter. So or say in K theory is the same. So in K theory, the current parameter associated to the C-star action, scaling action will be Q, and all the other parameters associated with the Cartan will be the spectral parameters. So there's already, we can see all the parameters seem to be matching nicely. And indeed, it's we know from Nakajima that the current K theory of such a space possesses the natural action of the Q, in this case AG, of the loop, the quantized loop algebra associated to that thinking diagram in this case. And in this case, we even know what the representation is. It's very easy. It's just the usual G+1 dimensional representation of GLN, of GL G+1, sorry. And you just enter it n times. And the Z play the roles of, again, they're parameters of the representation. But at the level of geometry, they're run parameters. So that's the that's the hard part of the construction that I'm not going to talk about at all. In fact, there's a second part of that story, which is equally complicated and which I will not give any details about either, is we want more specifically to identify geometrically what is the standard basis. In mathematical physics, when you think about an matrix, you think of a natural matrix, not a linear operator acting on some abstract space like the K theory of, of some quiver variety. So we need a basis for that. And so that problem was solved by Openkopf and collaborators, and K theory by Openkopf himself. So following him, we could associate to really a quantum integral system in the sense that we're used to in mathematical physics by choosing a particular basis of this K theory, equivalent K theory space. Yeah. Yeah, so I'll say exactly what I mean. Yeah, let me finish that little paragraph and then I'll answer your question. So the first thing is, you have this general construction, which is very powerful, which is called the stable envelope. And in particular, in the case of a variety with isolated fixed points, it gives you a basis of your space, like literally, like a good, honest basis. And then one way you can think about, so that's general theory. But in this particular case, there's a very natural way now you can think about the matrices. They just the matrices of the natural dot group action in this particular basis. So you just think of, in this case, the geometrically the matrix literally affects the action of the buffer. And then the Ambassador equation is the Frege relations about the symmetric group, and the unitarity relations is so all the relations are very natural in this very naive geometric picture. Okay, so now so precisely. So the construction usually goes as follows. So first you define this stable basis, then you define the matrices more or less in the way that I just wrote here. That's a more general picture for general varieties that is, in this case, it reduces. So you have the matrices. And once you have the matrices, the idea is very simple. You're going to use the RTT presentation that you love, And you're going to build the whole system this way. You're going to build the interaction itself by saying, it's the RT relations, and you will recover this way all the results of condition. So that was the idea of André, which was very suddenly made a lot of constructions very much more natural. It sounded more like the kind of stuff that I used. Now you might say, oh, but we don't really. Why do we need this new basis? We already have the Schubert basis, which is the one we like in cohomology. You should really think of this stable basis in the case of cotangent bubbles of the flag varieties as being some kind of Q deformation of the Schubert basis. So it's very similar in some sense to the Schubert basis. This statement can be made more precise. In particular, it's also indexed by by binary strings for the Grassmannian, let's say. So if you take the cotangent bundle of the Grassmannian, you'll get that this basis is indexed by binary strings. Or more generally, if you take these set flag varieties, it's indexed by D+1 array strings. So strings made of numbers between say 0 and D with macrotensions. And so these will be kind of the labels on the boundaries of my process, basically. But again, all these ingredients are not enough. So the next stage is in this language would be what about the interior of a puzzle? Where does the 10 come from? We had 3 labels, zeros and ones. We understand now they're related to the cohomology of Grassmannians, or maybe of that cotangent bundle. It doesn't really matter. Yeah, the cohomology of a cotangent bundle. Cotangent bundle can be. You can contract the fibers, so it's not like the cohomology actually changes, right? It's just so it's just more or less the same cohomology with maybe one more parameter, which is the scaling of the fiber. So we have the space, we have the binary strings or GRE string or so whatever on the boundaries. But what is the geometric or representation theoretic of what's in the interior of the puzzles? So the way we did it originally in our paper, our 2017 paper, was rather ad hoc. We kind of guessed that there would be a larger Hopf algebras such that the puzzle itself can be interpreted as an interpolar acting on tensor representations of this bigger Hopf algebra. And the way you should think about it, so this is a puzzle viewed somewhat abstractly, where I haven't actually written any of the labels. And I've also done something a bit funny. I've destroyed all the horizontal edges here, except maybe just at the bottom. And the reason that I did that is that this picture, you should always, in the usual language of mathematical physics, we tend to take the dual, but that means you imagine each time you have such a rhombus, you want to replace it with the crossing. And now the labels, instead of being on the edges here, are on the edges here. But it's strictly equivalent. So if you take the sort of dual picture, this already looks very much like the pictures we like in quantum interval systems, each crossing being an R matrix. So I've cheated, of course. I've broken this thing I've glued these things together to make R matrices, but I still have to pay the price at the bottom. There's another thing I can do here. These triangles cannot be glued with anything else. So there's going to be another interpolar at the bottom, which is an interpolar from a tensor pair of 2 representations to another one. And this one you have to define no matter what. And of course, you could say I could have not cheated when I kept all these vertical edges, and then would have in fact 2 interpolars, one from V1 tensor V3 to V2, and one from V2 to V1 with V3 tensor V1. So one way or another, you still need more intertwiners than just the general theory of quasi-triangular algebras is giving you. So that gives you constraints on which algebras can appear. In fact, our first paper has in its title something about trilinear invariant forms. So in the first paper, we assumed that all these 2 representations were kind of morally the same, not quite the same in general. I'll say a word about that. And then we tried to find algebras which had all the right numerology and all the right constraints on the existence of intertwiners. And we found that for d equals 1, 2, 3, 4, we found an answer. We found that if you treat this bigger algebra that sits that contains a sub d to be a2, t4, e6, e8, then this miraculously satisfies all the right properties. And in all cases except d equals, yeah, as I said, for d not equal to 2, these are literally the same representations. For d equals 2, this is d4, which has this triality. So these are actually 3 different non-isomorphic representations of the same dimension. But in any case, there's some very tricky numerology there going on, but we found some algebras which contain the original ones. And then we can apply some general traits that we find, and that gives us for free puzzle rules, essentially for those stable basis elements. So here's the precise statement. So in the original paper, we didn't write it this way. This is already the paper number 2. We understood what we were doing. So first you have to renormalize the stable classes a little bit. They're not linear. You can't take products of stable classes for stupid reasons that I'm not going to tell you about. So you want to have a class which is properly normalized. And so you have to divide by the class of the zero section of the convention bubble. So modulus some renormalization, if you like, of these stable classes. And in fact, once you've done this renormalization, they have a nice name. They're called motivic Segre classes. In particular, they have some nice motivic properties, which I don't want to talk about today. But anyway, so these are nice classes for taking products. And then the theorem is that these puzzles we're building, they're literally computing for you the product of such lists. So that's paper number 2. We said, okay, we can, so you take this kind of abstract puzzle like this, you fix the parameters in some spectral parameters in some clever way. There's some funny business going on with some, it's not on the slide, interesting. Wait, I can salvage this. No, it's actually really just too low. You can't read it. Okay, there are some parameters missing in the theorem which you can't see. Oops, I must have changed the format. Okay, it doesn't matter. Kappa is some. Again, there's some funny numerologies. It's a cubic root of q to the power the dual constant number of the algebra or something. So that there's some very fine tuning of the spectral parameters, if you like, in this picture. And then the claim is that if you compute this as an intertwiner, it's entries in the sort of natural basis we have of this space is computing exactly for you the product rule of these motivic Segre classes.
Oh, so you can not full size of the screen and maybe show the lower part.
No, I think I actually screwed up and it's actually out of the slides. It's because I think at the last minute, like half an hour ago, I decided to change the color scheme and the presentation and everything, and it's screwed up.
You can show additional.
What's that?
You can show additional text.
No, it's okay. You don't need to know all these gory details anyway. Oops, what did I do? Right. Now, as I said, so these classes you should always think as some kind of cutiform versions of Schubert classes. So if you really want to compute Schubert classes, which is what we did in the original paper, you have to take the limit q goes to 0, which is a bit of a funny limit to take for, when you have like uq s hat or whatever, or in this case, uq d4, e6, e8 hat. So you have this slightly tricky limit to take q goes to 0. And so we did this computation explicitly in the first paper. So the easy part is that these S lambdas become just Schubert classes. The hard part is to get the actual combinatorial rules for the puzzles to work. So you have to take the limit of all the matrix entries of all these intertwiners, and that's a bit tricky, but we did that.
The usual crystal.
It is not the usual crystal limit. It's more complicated than that. No. Yeah, that's a good question. No. If you like, at the level of the underlying AD model, it's like going from 6 vertex to 5 vertex, whereas crystal would be more like going to 4 vertexes. So it's a slightly more subtle limit where you have to. So first, really the way you do it is you twist first with the Greenfeld twist, and then you take the limit, and all the subtleties in taking the twist correctly. And so it was a pretty tricky procedure, but we did it. And for d equals 1, 2, 3, we got a nice explicit combinatorial rule for products of Schubert classes and the corresponding partial flag varieties. Unfortunately, for d equals 4, it doesn't quite work. The rule is not positive. And even for d equals 3, it's not positive equivalently if you don't care about such things. I haven't talked about the equivalent generalizations, but so there are unfortunately some annoying subtleties, but only interested in taking the limit. So it's very pragmatic issues. But of course, combinatorialists like positive rules, and unfortunately, even though we do get a rule, it's not positive for d equals 4. So in other words, you're writing some of them, not as just a sum at once, but sometimes there are negative things, and so that's not so nice. So finally, so the other important thing we understood after the fact is that there is actually a natural interpretation of the geometric. There's a natural geometric interpretation of why we need this bigger Hopf algebras, which in the first paper we just put up in an ad hoc manner. And so I don't want to say too much about it, but the basic idea is because you're working with cotangent bundles, you can't just expect to just, what is a product rule? A product in cohomology is like taking the pullback by the diagonal embedding. So x goes to x cross x, and then you take the pullback. That's the product. That's the multiplication rule. But when you take a Cooper variety its Cartesian product with itself is not really a quiver variety, and maybe you want to replace, x cross x basically with a quiver variety, and that's exactly the point. So you're working side to side at D, then you say, well, I kind of want to have something that's like T star D cross T star D, but that's not right. That's not a quiver variety itself. So we're going to embed this in a larger quiver variety in such a way that this appears as the fixed point set of some nice C star action. And so that's really the way you should think about it, where it's basically we're trying to do some geometric operations, but maybe we need as an intermediate stage to embed things in a slightly larger variety than we expected at first. It's a bit vague, but very explicitly, that means in particular, also the other important idea is we want to do everything using Lagrangian correspondences. These are all symplectic spaces. You don't want to just randomly do some operations. You only want to deal with Lagrangian correspondences, and then so sort of embedding this inside this as a fixed point set means really, so part of the stable envelope construction basically tells you that when you have a fixed point set of a quiver variety, you need to have natural map from one to the other. So that's the map that's going to first kind of move things from the product of two flight varieties to this bigger ambient quiver variety. And then the interesting part is what happens when you, on the contrary, try to get back to the original T star T. So that part is new. And that's what we call in integral systems the fusion procedure. And so as a corollary of this construction, we recover something that I have been working on for some time on my own, which is the geometric interpretation of the fusion procedure of quantum integral systems. And so we get it here in the fairly general framework. I had done it before in a more specific. So anyway, at the end of the day, the point is that we can reproduce the whole construction, and in particular, the proof of the puzzle formula in a purely geometric matter as a series of successive Lagrangian correspondences. And yes, just technically, we only in cohomology. In K-theory, it should be the same, but there are annoying issues with the Lagrangian correspondences in K-theory, which I'm not an expert on, and we've decided to write the paper only in cohomology, but that's a minor technical detail. The philosophy should be true for any cohomology theory, or possibly even for elliptic cohomology if you care about such things. Okay, so in the final part of the talks, I have like, what, 10 minutes left or less?
You have 10 minutes.
Yeah. So here's some applications. So our further results. So these are all from papers which are not yet on the internet, the archive. So the first thing to notice is there was this weird sequence of algebras occurring in our construction, A2, D4, E6, E8. And yeah, I should point out that at least naively, we only have quiver varieties for simply linking diagrams. So let's not go outside ADE. Let's stick to ADE. I'm sure there are versions which are non-simply such as, I mean, both of the quiver varieties and our construction, but for now, let's just stick to ADE. So even there, you can say, what about Schubert calculus interpretations of other ADE quantized loop algebras? And the answer is yes, so there is such an interpretation. If we allow multiplying Schubert classes to sort of be from different flight varieties. So for example, in the case of AN, something we have already known for several years, we've announced this result already 3 years ago, but the paper is still not, well, it should be on the archive hopefully in the next 30 days, let's say. So that's fairly easy to understand what happens in type A. So the puzzles are actually very, very simple. They correspond to just the fusion of Cn tensor Cn to alt Cn. So like the one box to two box vertically. So just yeah, the anti-symmetrizer basically of the Cn representation of Qn. So it's an extremely simple model in which you basically have pieces where they have labels which are integers or blank on the northwest and northeast side, and you have pairs of integers or single integers at the bottom. But really, single integers you can think as a number and a blank basically. So always pairs of integers or with a blank possibly. And the puzzle rules have certain inequalities, which again occur in the limit when you take the limit if you go to just to 0. And then you take these puzzles, you put them together, and they compute the structure constants of basically, you take classes, Schubert classes from partial flight variety, but then you pull them back to the full flight variety, and then you take their products. So the way you should think about it is we're working in the full flight variety, but we're not allowed to take the products of arbitrary classes, only those that are pullbacks of some partial flight varieties. So it's a rule that's what it is. Here's an example of what the puzzles look like. It's nice to, instead of using numbers, use colors. So each color represents a label. And then you have basically a like path coming from the two sides, kind of intertwining, and then they nicely form a nice full set at the bottom. And then there is some complicated combinatorials to read the labels on the three sides. This is lambda, this is mu, this is here, but if you decode it in the usual conventions that people use in the, say, Schubert polynomials and stuff like that, this is a natural identity satisfied by Schubert polynomials, or if you prefer an identity in the cohomology of the full flag of C6, which is already bigger than anything one knew how to do before. So that's for AN. For GN, the thing we've done most recently, that was in the past year, and we're finishing. It will be in the same paper that should come out very soon, is to do the DN case. The DN case is kind of interesting. In many ways, it gives us the most general rule for products of Schubert classes or product of Schubert polynomials that we know of. And so DN is the SO2N algebra. And the corresponding future rule, so you know, there's the three spaces. Maybe I should go. Yeah, maybe I'll use once. Very strong. So the most important ingredient is to find this intertwiner. So the intertwiner in this case is just spin. So there are two spin representations of the spin plus spin minus that goes to the vector representation. So that's the intertwiner we use to build puzzles. Basically, so just yeah, I mean it's the same that on the slide. I'm just redrawing it pictorially. Now the interesting thing, so the spin representations have a cardinality which is a power of 2, and you should think of it as like now you have lines that can kind of be stacked on top of each other, so that that you have n-1 types of lines, and they're arbitrary. You know, they can all be on the same spot basically. So it's all subsets of something of cardinality n-1. I think I'm going to skip the blah blah about how to actually decode this, the labeling, because that's too complicated. So anyway, here's the theorem. So now, as I said, you have triangle puzzle pieces in which the northwest and northeast edges are now indexed by subsets rather than by just integers. However, at the bottom, this is the vector representation, so it can only have just a single number or special numbers called even and odd. So there's some fairly complicated combinatorials going on, and here are all the pieces. Yeah, so let's see. I actually have to read it myself. The puzzle labels are subsets. On the horizontal sides, they either up I, down I, or even or odd. And then the puzzle pieces, the down I is pretty clear. It tells you that the I that kind of dropped here and all the rest went through. Up J means there's a J that went through, that went up, and then all the rest went through. And even in odd special cases where there's either nothing or there's one line going, and then 180-degree rotations. And if you do this in K theory, sorry, I haven't used the language of working polynomials. If you do it in K theory, you have more triangles. If you do it with motivic Segre classes, you can have even more triangles. It's a fairly complicated rule, but it's completely explicit. I've only drawn like on this slide 2 examples of the product of, so in terms of Schubert polynomials, that would be like taking the product of, S 2543167 to S 4132567. So it's already in the full flag variety of C7, which is pretty big. And you can see how things are getting really messy. You have like lines on top of each other. But the rules, I mean, I checked it by computer very, very extensively. And of course we have a proof, but such proofs can be wrong. So I only drew 2 of them. There's like, well, you can see there are 1, 2, 3, 4, 5, 6, 7, 8 of them or something. And so you get such identities for free. And the final thing, which is something that I've been announcing for many years, but it still hasn't been published either, is the fact that it also gives us for free, the geometry gives us for free proofs of associativity. So I mentioned already the fact that when you have structure constants, they have to satisfy certain constraints. And so one of the constraints, like the only constraint if you're not worried about commutativity, is associativity. It's the fact that if you take triple products, it has to be associated. And very explicitly, if you write this triple product explicitly, you get such identities, quadratic identities for the structure constants, which are very easy to understand graphically. It's like gluing together kind of like 2 triangles. And while splitting, actually, wait, isn't there? Yeah, that's supposed to be an animation. This is a manual animation. Anyway, so it's like splitting a square in 2 different ways, basically. This is the way we think about associativity in sort of pictorial way. And these, of course, pictures, you can literally think of them as puzzles. And so it's basically telling you that you have pairs of puzzles that agree on the common edge, you'd be able to instead replace it with pairs of puzzles where the division is very good. And so, in general, this whole integrable/geometric framework gives you an answer. It gives you an answer which is like linear algebra. It will tell you some linear algebra that turns one into the other. Though in some cases it's even a there are natural bijections. So unfortunately, we're probably stuck in the same. But maybe again, the internet is going to save us. I don't remember this. Oh yeah, well, it works. Well, it might take a long time to load there. Anyway, yeah. So we know also how to do. So we know this is the example of just Grassmannians. So in the case of Grassmannians, we can. Yeah, it kind of works. Can we make it bigger even? Yeah. So in the case of Grassmannians, we know exactly. No, that was pushing it too far. We shouldn't. Okay, maybe we shouldn't worry about it. Anyway, so yes, so we know how to do it explicitly for all type A, AN, in particular Grassmannians. We have some very explicit rules that allow you to turn pairs of type A puzzles into other pairs of type A puzzles. I'm still wondering about the type D case. I haven't figured it out yet, but even though the general formalism there are some technical issues which I haven't resolved yet, but which I hope to resolve in the near future. I think I should stop here. Thank you. Okay, fine.
Can I ask you, are you here in system? Understood, but here all based on the theory of integrable systems. Very integrable systems except non-partition, but non-partition is two small parts of the integrable system. Very integrable system.
What is a quantum integral system? You know, you can build everything out of the R matrix. So yeah.
Are there any combinatorial ways to describe the spectrum of corresponding absolute?
Well, that's the thing, right? So where are the constituencies? I guess would be the first question. The transfer matrices are kind of hidden there. They're not really. The transfer matrices are the operators of multiplication in the cohomology, but.
Well, there are plenty of examples because there is no general theory. I think the question is whether it's, I mean, this beautiful combinatorial descriptions of whatever can be described this way, it can be used to describe the spectrum.
Yeah, so for example, that's the way. The short answer is no. We don't really. Not only don't we have better equations, we don't really need them because you see.
No, I think it's the second order question. I understand that here it's not about transformation.
Right. I mean, there's no simple answer to the question. I mean, the short answer is of course no. We don't compute spectra of any here. But there's a more subtle question like where are the basic equations hiding here? It is absolutely true that if you really think of the cohomology of say, or even the quantum cohomology of say the Grassmannian, it will be. I mean, it will have the basic equation encoded in there, but. Yeah, it doesn't really play any role in my construction for some reason. It's a slightly tricky point. I don't have a simple way to answer this.
I have an easy question.
Yeah.
So this, in some sense, this is related to very much to the combinatorial representation.
Yeah.
Just legal issues and rules.
Yeah.
So, and then bring it up to the level of. Let's say if you specialize these things through the unity or the finite, then the representation theory is not so much simple.
Right.
And you have the stilting integrators, stilting models. So we think there is a similar expression for the robustness of multiplicities for tilting models.
Oh, okay. So The first thing is that I only know how to deal with the solution of the electric equation since I am difference equation. So if you tell me about error plots, I'm going to tell you I have no idea how to deal with this. But if you stick to those,
I would say quantum is cool.
Right.
Well, obviously,
No, we need that fine, right? Quantum affine.
okay.
Yeah, but you know that, for example, you can get all these weird cyclic representations and data.
No, they're not secret representations. So they're very powerful.
Yeah, that should work. I don't think. So what does it mean to take rid of the virtue? It's like you're instead of taking, so geometrically it's weird. It's like saying you're replacing the scaling action by a discrete action by multiplication by root of the, right? So
Okay, no, maybe.
no, so this is, I would say it's a looking problem. I think nobody has looked enough detail. It might be very hard, but it sounds, yeah, that could be something like that.
If there are no other questions, I